One application which uses exponential functions is half-life. And half-life is defined as being the amount of time it takes for a value or quantity to decrease to half the original value or quantity. And the implication is that it will be decreasing exponentially. So we have an example. Carbon-14 has a half-life of 5,650 years. And the exponential formula we can write generically as P of t is equal to P0 e to the kt, where P of t is the current or final quantity and P0 is the original quantity. If we write this as a ratio, we can compare the final quantity and the original quantity. So we divide both sides by P0 and get this ratio. And in this case, our ratio is equal to a half. That is that the final quantity is 1/2 the original quantity. And now we can set this equal to e to the kt. And we're told that the amount of time that it takes to decrease to half of the value is 5,650 years. So we can then write this value in for t. Next, what we want to do is solve for k. But in order to isolate this, we have to get it out of the exponent. And so we can do this in one of two ways. One way is because our base of our exponent is e. If we take the natural log, which has a base of e, we take the natural log of both sides. On the right, we end up with natural log of e to a certain power. And remember that log base e and then e to the power, the log and the exponent will cancel. So actually what we end up with on the right-hand side, again with log and exponent canceling, we simply end up with 5,650k. So now it's relatively straightforward to solve for k. We can calculate natural log of a half, and that's equal to negative 0.693. And then solving for k, we're going to divide both sides by 5,650. So we can use a calculator to figure out that value, and we end up with a very small number. We get then that k is equal to negative 0.00012, or 12 10,000ths. Now that we've got a value for k, we could actually rewrite this equation. And here we substitute our calculated value of k into the original equation. This time we're told that 6% of the original amount of C14 remains. And so we're not actually told how much we started with and how much we ended with, but we know that of the sample, 6% is the original amount and the rest has decayed. And so this ratio, P of t divided by P0, is going to be 6%, and we can put it in for that fraction. And now we've got our exponent here set equal to a decimal number. Just like before, we can take the exponent and bring it down by taking the natural log of both sides. So again, natural log of e raised to a power just eliminates the natural log and the exponent and brings the power down. So we end up with natural log 0.06 is equal to the natural log of this exponent. Again, with natural log and e to the power canceling out. So simplifying on the left, we end up with a negative 2.813. And notice, because we are taking the natural log of a very small number, remember log of base e means the power needed to change e, which is about 2.817, into this very small number. That's going to need to be a negative exponent because, again, the negative exponent is going to cause our number to be a fraction. So we end up with a negative number on both left and right. And finally, we can solve for t by dividing by the coefficient. And isolating the t, we can cancel out these factors. And this number on the left actually ends up being a much larger number because we are dividing by such a small number. And using the calculator, we get that t is equal to 22,948 but I'm going to round this off to 3 significant figures because our original value of half-life, 5,650, had only 3 significant figures, and this number is in years. We can try to get an approximate sense of this figure by taking a look at our half-life of 5,650 years. Let's call it approximately 6,000 years. So in the first passing of about 6,000 years, we would cut in half, or go from 100% to 50%. In the second halving, we would go from 50 to about 25%. In the third cutting in half, we would go down to 12.5%. And in the fourth period, we would go from 12.5 to a little over 6%. And so that's somewhat comparable to the original 6% that we're looking at. So we can see that we have cut in half 4 times to get to this place. And that means that 4 periods of 6,000 years should have passed. So 4 times 6,000 would give us approximately 24,000 years. And that is comparable to what we have actually calculated more precisely.